turn on your videos. Perfect. Okay, so let me introduce to you our next speaker, which is Nicola Dondi from the University of Bern, and he will talk about resurgence of the large quantum number expansion in the O2N conformal field theory. So Nicola, please.
Thank you, Donny. So let me thank the organizer for giving me the possibility to speak here, to talk about this work, which actually might deviate a little bit from the main lines discussed so far in the conference. But I still hope that you're going to find at least some part of it of some interest and maybe even some applicable in your own research. So this is work which is based on, if you want, two papers. One is from 2020, and basically it was worked out by some authors, Gomez, Orlando, and Reffert, regarding this large quantum number expansion in the O2N CFT. And at the beginning of this year, I joined the same group in Bern, and together with Ioannis Kalogerakis and two of the same author, Orlando and Reffert, we started looking at some resurgent properties of the result they found. So I will basically, my talk is going to be organized following this title backward, trying to explain every keywords, starting from what is like simple grammar slide of what are CFTs, on why I want to look at this specific example of the O2N, what I mean as a large quantum number expansion, which from now on is going to be called the large charge, it's just to make more clear. And maybe I tried also to be a little bit more general in the discussion about resurgence, being a more general technique for a large variety of problem. And these large quantum number expansion is just an example that you might enjoy, you might not, but just to say that these methods are more general than that. Okay, so let me start by motivating to this audience why CFTs are of relevance in physics. Well, I don't really need to probably, but just let me say that conformal field theories in modern physics are basically everywhere. You can find them from the study of RG flows in quantum field theory all the way up to string theory and holography. So the relevance is there, of course. And they are, if you want, slightly more complicated models than topological field theories, but still simpler than ordinary general quantum field theories that make them tractable. So let me start with just my working definition that I will have in mind for the rest of the talk. For me, a CFT is just a quantum field theory on RD, and I will consider mostly D equal 3, but in general, D higher than 2. And I will always consider to have, for this field theory, my conformal group, which is SOD plus 1, 1 in this space-time dimension, and an internal group, which is always, for me, is always going to be continuous. So this is always a Lie group in my case, and not a discrete one. And I will show you why I want this. Generally, CFTs can actually be defined just by a list of data, right? You just need a list of primary operators and a set of numbers that tells you how they combine inside the correlators. You have scaling dimension deltas, which actually fix completely 2-point functions, and OPE coefficients, which fixes 3-point function. I will mostly talk about computation of scaling dimension here and completely neglect computation of OPEs. So let me say, what do we mean to solve a CFT? What do I mean by that? Is just simply compute, given a list, the list of these operators you start with, just give me all these possible numbers so that I can have all possible observable out of this theory. And generally, this is not such an easy task. There are methods that are consistency based, so it tells you like on general grounds how these numbers should relate to one another. And these are sort of important because they might tell you also that fixed a list of primaries, then the number of possible CFTs with that list is sparse, is only like discrete sets. But maybe from a more Feynman diagram QFT friendly perspective, one might think of perturbative methods. So basically start from a CFT that you know how to solve, which is always the free one, basically, where you know the full spectrum and all the data, and deform it slightly via, for example, large N or a change in dimensionality to actually connect it to another CFT, which is initially perturbatively under control, but at some point it might be beyond this perturbative expansion, and then you don't know what to do, essentially. So let me actually talk about a very specific CFT, which is the O2 vector CFT in 3 dimensions. So this is a CFT that actually appears often in nature, for example, or in general models. For example, it describes the critical phase of the 3D XY model, so spins moving in only a plane, but is also describing the critical phase of helium-4 when it goes through a superfluid phase transition. So it is, if you want, it is relevant also like physically. One way to describe this CFT is just, for example, by starting from O2 scalar phi-4 theory in 3D and deform it with a IR relevant operator, so exactly this phi-4. So you can show that in general, if you don't introduce any other control parameter, these deformation will trigger an RG flow, sending you from ultraviolet completely free CFT, of which you know everything, to an infrared strongly coupled CFT, which is exactly the one that describes these phenomena. Okay, so this is actually the working definition that I will consider just via deformation of a free scalar phi-4 theory. Let's say that from this theory, what we want to know, what we want to compute are scaling dimensions. Okay. And the most convenient, well, a convenient packing of all of this information is a specific partition function, which is obtained by just while transforming R3 to a cylinder and compactifying my time direction. This is actually, this is just called a thermal circle. And you're going to see a lot of terminology from thermodynamics going from now on. So I better start now, basically. You can easily show that this partition function actually knows about all the scaling dimension of the primaries in our model. So if I'm able to compute this partition function, taking, for example, a large beta limit, a small temperature limit, then I will be able to compute all this information in once. Right. So what do we mean by then a large charge expansion? Well, this CFT has an O2 symmetry, so it has an associated charge Q. And one might wonder, why don't we just try to see if there is some simplification in computing such partition function? If we just slice the sum over the Hilbert space, just keeping only a subsector that fixes that charge, right? So if you want, like naively, just is inserting a functional delta function, whatever that means, but maybe more practically means of summing over only those primaries with that quantum number. There may be more than one, of course, because no one guarantees you to have only one for that. Basically, the main statement of large charge goes as follows. This is not, maybe it might be slightly unknowingly phrased, but let me just say it this way. So it turns out, this is actually an assumption, that in the limit in which you take this charge to be very large, then this partition function can be realized instead of your UV scalar fields, those scalar phi-4 theory, in terms of Goldstone bosons, which realize a specific pattern of symmetry breaking. It's a symmetry breaking that is more complicated than the one that, for example, you find in a Higgs model in the standard model, because it also takes into account space-time symmetry breaking, okay? And actually, this cutoff or this EFT scales like the charge that you decide to fix, okay? So taking these as a fact or as an initial assumption, you might ask, okay, how many ways do I have to realize such an EFT, realizing this particular symmetry breaking? Well, there are not that many, and there's only one basically that is computationally viable, which is the conformal superfluid approach. Okay. So let me just say what actually this approach leads to. What is the main prediction of all of these assumptions in one? Is basically that you're always going to have a primary, which is the lightest one once you fix the charge. And this scaling dimension actually has a very particular scaling. In 3 dimensions, it scales like q to the 3/2 as a leading power in the charge. And it has a downward series, a tail that goes in inverse power in 1/q, and possesses, funnily enough, a universal constant. What do I mean by universal constant? Basically, all of these coefficients in these expansions, you cannot compute them from first principle. If you know how EFT works, basically you know that you're always going to have these Wilson coefficients, which are the numbers that you put in front of your effective operators in your action, which depends on the UV theory, which in general you don't have access to. This makes it effectively an effective approach. So the scaling is actually a prediction, and this universal constant does not depend on any of these numbers. So it's actually universal if you want. So what does it mean? I just draw on this picture what actually this means. So you have that for every fixed charge, right, you're always going to have this minimal scaling operator following this law, and then on top you're going to have another spectra which might be not evenly spaced, and they could be anything. This prediction is only for the minimal one. And actually, I basically draw on a Monte Carlo simulation, which actually was done to verify this scaling in this particular model, in this O2 model. And you can see that actually this fit is actually very fitting. And they were able to estimate from these simulation values for this Wilson coefficient. And they were able to show that actually this prediction seems to be really realized in this regime. So these were some of there are some features of this result that basically triggered all the research that we have done later. So first is basically, I have a universal constant, which in this scaling is a q to the 0 term, and is universal. It has also been shown that in even dimension, this gets replaced by a log q term, which also has a coefficient which is universal as well. So one of the questions that we had is, depending on the behavior of the tail in this expansion, there might also be universal terms that are non-perturbative in nature, in the sense that they go like e to the minus q to some power, which doesn't have a 1/q expansion, is non-analytic there. So in that sense, is non-perturbative. On top of that, these Monte Carlo simulations show that actually this scaling behavior, which is meant to be valid only for very large charge, can be extrapolated quite effectively to small charge. And this might be somehow surprising because it's a large charge limit, right? So one of the way we wanted to explain why this happened, and this is related to this presence or absence of these non-perturbative terms in this expansion. So basically on how to sum the rest of the tail of this series here. So unfortunately, as long as we have no other control parameter, the study of this expansion is very limited, just because we don't have access to these Wilson coefficient, simply as that. So what has been done was to introduce an extra order parameter, which is just an n taken to be large. One can, in fact, just extend the O2 model to a O2n and actually look at the sector in which charges are fixed only according to the maximal torus subgroup of O2n. This is a choice that one can make, and is probably the simplest that still keep these charge fixing abelian, even though I now have a non-abelian group. Right? And this is a specific double scaling limit in which you take both Q and N to be large, but Q is the dominant quantum number. I will try to briefly sketch what is the result over there, just as a technical remark, and also to introduce some more thermodynamics friendly notation. It's actually more convenient to shift from a canonical point of view in which your partition function, is just an exponential of your free energy, which is simply the scaling dimension you want to compute, to a grand canonical picture in which you trade your charge quantum number to a chemical potential quantum number. And the role of the scaling dimension that you want in there is played by a grand potential, omega. And the relation between the two is just a Legendre transform, which is suffice to say for the moment that is in one-to-one. As Q is large, it also corresponds to mu being large, so it's monotonic. So in the grand canonical ensemble, this large charge limit is realized by a large chemical potential limit. The miracle, the simplest computation in large N gives you a very neat result for this grand potential at the leading order, and it's just would-be Casimir energy on a two-sphere. So the two-sphere, recall, is still the space manifold, and on top I have a thermal circle. So this result is not exactly a Casimir energy, but it corresponds more to the case in which you basically dimensionally reduce the thermal circle, and then you obtain only a sum over eigenvalues on the sphere. This is just to say that the result, all of these, is still in 3 dimensions, even though from now on it will always appear the two-sphere. You know that this sort of results, just given in terms of zeta functions, which maybe I should add that as long as D is odd dimensional, they don't need further regularization. They always can be related to some heat trace over your space manifold. So here the main trick to compute this grand potential is to look actually at the asymptotics of a very simple observable, which is the heat kernel trace on a two-sphere. And this is sort of well known. Actually, you can already see from this integral representation of the zeta function that if I want to take mu to be very large, so my large charge limit will correspond to small time elapsed by my heat kernel on the sphere. And vice versa, if I want a small chemical potential limit, which turns out to be reachable as well, thanks to being in large N, this will correspond to long time elapsed. And the asymptotic regimes are actually very well known. Well, in the mu going to 0 limit, this is just a leading exponential. And this actually gives you a convergent expansion in mu, in small chemical potential for this quantity. So over there is not much surprise. And this is sort of actually expected from the simplification that large M usually brings. However, in the opposite regime, in the infinite chemical potential, this is the Sig-DeWitt expansion of the heat kernel, which is known to be factorially divergent. Okay, so we expect this large charge expansion to be asymptotic from now on. Actually, one can retrace back all of these passages going from the heat kernel to my grand potential to my scaling dimension via Legendre transform, all the way back to my scaling dimension. Unfortunately, here the result is not nice enough because the only way to invert my Legendre transform is term by term. So here you have 2 expansions, one for a small charge and one for a large charge. But the coefficient needs to be, they actually can all be computed symbolically through Mathematica, but after some terms it becomes unbearable, so you just need to go numerics. And the small, is nice to see that the small charge expansion actually matches a 3-level result for a well-known operator, which is just the mod phi to the q. So as long as we take this large n limit, we also know what is the form of this operator in terms of our phi field, which it usually is not. And on top of that, there is actually a loop expansion. This is a proper loop expansion in the phi theory, which turns out to be convergent with coefficient is Bn. On the other hand, in the large charge regime, one actually finds the correct scaling that was conjectured by this large charge effective field theory approach. The only difference is that here we don't employ this EFT approach, because in large n everything is Gaussian already. And you can then ask, what is the behavior of this Cn? We expect a factorial growth. But which sort of factorial growth one actually should look for? Well, already from the analytical result, you could see that, for example, exactly that the ground potential was a double factorial scaling, so m factorial squared. Here, you could argue that delta goes the same because a Legendre transform should not change your degree of factorial growth. Or otherwise, if you're lazy, you just do like a simple ratio test in which you prove numerically that even though this convergence is actually to this asymptotic behavior is kind of slow, you can accelerate it through numerical methods via Chang transformation and actually prove that this actually is double factorial in growth. So this, if you want, is one of the main results that I'm gonna elaborate further afterwards. And in large n, it seems to be general enough that this model has n factorial squared, not n squared, sorry, growth in this large charge expansion, and we can know all the coefficients basically. Now, it might be then, we might be tempted to assume that also there is a general feature of large charge on the main ground that usually a large n limit, once expressed in a proper Feynman diagram expansion, actually cuts a lot of terms order by order and actually improves the convergence. So one can say that this is at least n factorial squared. Of course, there is no way to check this other than numerically, but it's a reasonable assumption if you want. Another, something that might not be very much known is that every time basically you have a factorial growth, this is a symptom or a signal of some non-perturbative corrections in this expansion. Basically, if this growth was just a convergent, it's very easy to sum this series and extrapolate my result to any charge that I want. Just by summing it, if I am beyond the radius of convergence, I use other numerical methods, but there is no obstruction to this. However, if you want to do the same for a factorially divergent series, you know that the radius of convergence is 0. So you cannot sum it anywhere. You need something more refined to obtain a closed form result, something you can extrapolate in this case. And for these, you need this set of methods which are sort of technical. So I will just flash some of the key ideas, which are all known under the big name of Resurgence. And they basically tell you how to do this. So how to sum these factorially growing series. So like generally consider my observable, which is a scaling dimension or anything that can be. This is a very general approach. And just take me like an expansion in inverse charge, which is easier to track. Now my expansion parameter asymptotes to 0 instead of infinity. And suppose that this has a series representation that you can compute order by order, but it's only formal in the sense that my coefficients are factorially growing and I cannot actually sum, okay? So the main device to actually try or give a meaning to this formal series is called the Borel summation, and it works as follows. So basically, just take your factorially divergent series and divide out the factorial growth. Try to obtain somehow a convergent series out of it, right? And in this example, I just divide out by a gamma function of beta n, which exactly cancels out a factorial growth as bn factorial, okay? You might want to also add an offset b, which sometimes simplifies and make it these sum closed form resummable, but it's not unique. You can have more than one of these Borel summations, okay? And as long as you divide out the complete factorial growth, all of them are fine. Now, a further operation that you can make on this Borel transformation is actually an inverse Laplace transform. So integrated over array in this plane, the theta plane, which is also called the Borel variable Borel plane. You just decide an angle to integrate along, integrate with a given measure, which depends on the specific choice that you made for Borel transform. So your choice actually comes back here, but you have an exponential type weight, which does not depend on that choice. It only depends on the on how fast the factorial growth is. Okay, and you can show that this integral, if you now plug back your definition of Borel transformation and wildly permute integration with sum, and no matter what theta is, on which ray you're along, you're always going to get back these asymptotic expansion you started with. So, however, this is an integral form for a complete function. So there is no a priori reason this could be computed for any z, not small, and should give you a result. You just plug these into Mathematica, you compute this integral, and you get a number. Thing that your asymptotic series was not able to do. So it might be an improvement, but there is a catch. So first, the catch is that you introduce a variable theta, which you don't know. So there might be more than one of these summations. So let me just tell you a little bit of information like how this theta dependence shows up. So let's just take this form that I give you, this integral without knowing anything about it. So of course, as long as my Borel transform, this b is not singular around the theta ray, this integral is well defined. And actually, in Z, defines a function which is analytic in half planes, right? So if I have an angle θ2 that I choose, then this function is well defined and analytic in the lower plane. If I choose another one, this one gonna have another plane which is well defined. You can show that if in the Borel plane your Borel transform doesn't have any singularity in this cone between these two angle θ1 and θ2 that you chose, then actually is regular all over there, and you can analytically extend it in the joint domain. So in this way, you can always extend this integral from a cone, from a half plane to an inverse cone. Can you do it everywhere? Well, you should not, right? Because if you're able to continue this, it means Borel transform doesn't have any singularity, but these would go against your initial hypothesis, mainly that your Borel transform was a convergent series. It has to have a radius of convergence somewhere. So there has to be a ray along which this Borel transform has a singularity. So what you do over there, well, the only thing you can do is ask, what if I integrate slightly below or slightly above that, that direction, and try to see at least what is the difference. These will define two different functions, and I can for sure compute the difference between these two. It turns out that this difference strongly depends on the singularities that the Borel transform has. actually, if you have simple pole singularities, this would actually be purely non-perturbative. It's going to be an exponential of the form e to the minus 1 over z. So these two functions, they differ by a non-perturbative term. And this is fine because this term is identically 0 once you force this to be a power series. So if you want, this all gets annihilated if I really go back to my original asymptotic series. So this is somehow expected. However, you might then ask, how do I get one summation out of it? It seems that I have a dependence on theta, maybe not as continuous as an angle can be, but there are some discrete values depending on which singular direction. Well, if you really think of this summation as a map, the usual trick to make it a one-to-one now is to extend the domain, okay? And recall that we started with a domain which was only power series. Now, instead, I extend it to what are so-called trans series. And trans series are actually something sort of natural that appears in, for example, a saddle point approximation of integrals. You have a perturbative series, which might be asymptotic. And on top, you have instanton type contributions. So if you start from a perturbative series, you might want to add all of these non-perturbative part with a given constant, which you don't know what it should be, but counts the number of non-perturbative part that you have. The exponentials now are instanton type. If you want, in the language of physics, they're just what you get from instanton calculus. But all of these can be generally be multiplied by a fluctuation around it, because you can't have fluctuation around the instanton configuration, and this will provide a new series that appears here.
Okay, I think we will have
some.
Yes, you have some technical problems.
Yeah, now I think can you hear me, Donny?
Yes, now I can hear you. You were frozen for a short
Okay, perfect.
period.
Yeah, I have
now
like
it's
a moment
better.
off.
Yeah, now it's better. Okay,
Good.
Please continue.
Okay. Yes. All right. So all of these series, these are all new series that are all factorially growing, and one can define a joint summation for this. And the summation works very similar as before. A Borel transformation applies separately to each series, to each instanton sector, and summation as well. So this becomes a summation in all sectors separately. And the price that you're paying actually is to introduce a new extra constant, this trans-series constant sigma k. However, you can actually see you have to have a way to fix them somehow, because otherwise there is no sense in which you can say that this summed trans-series is actually your result. Is your result that can be extended to all possible your starting variable. How do you do that? So this, it goes into like goes a lot deeper than that, but let me just tell you the way.
Okay, Nicola, can you hear me?
You know which non-perturbative correction you should include.
Sorry, there was again a freeze.
It was again freezing. Oh my God.
Yes.
Okay.
No problem.
Really sorry about it.
Don't worry. You may want to try with the video off. I mean, it's
maybe I can try with
usual,
that.
but probably then it's smoother.
Let me see. Okay, let's try like this and see how it goes. Okay, now can you hear me sort of well?
Yes, now it seems good.
Okay. Okay, so what happens here? So the main one of these results of this analysis is basically the form of non-perturbative correction you have to include are the same that appears in the discontinuities along singular lines of your Borel transforms, the one that I flashed before. These are the main form that you should put. Then the jump across these singular arrays is actually captured by these new constant that you included. And they are actually just jumping by integer powers of these SK parameters, which are also known as Stokes constants. Not really relevant for what comes up. The relations, which basically tells you that if you know the perturbative series to high order enough, all the constants that you see in this trans-series expansion can be computed with the accuracy that you want. As many terms you have in the perturbative part, the more precise you're going to be in the determination of all these further parameters. So in these unique result for you that completes your perturbative series, these trans-series constant. These are defined the modulus these Stokes constants, but they still need to be fixed to a given number, because these dependence must drop out. Okay, and depending on the problem, you might choose some other ones. I will briefly use in this large charge expansion afterwards. But first, just let me tell you briefly what happens in our case. So in our case, everything can be related to the computation of these heat kernel trace. And the Borel transform of the perturbative expansion, which is just the Seeley-DeWitt coefficients, is actually very simple and has only singularities along direction direction 0 and pi, all at my.
Yes, we keep having these problems.
I'm really sorry.
No, I mean, this happens. This is the drawback of virtual conferences, I think.
It's the usual. Yeah, also being back in Italy also doesn't help with the connection. But okay.
Okay. Yeah, I will just let you know which one was frozen. So yeah, we can continue from the second point on.
Okay. Basically, the tracking all the way back, these trans-series structures gets propagated all the way to my critical exponents, and they give a form of this kind here. If you want, this is the main statement of this analysis regarding this large charge expansion. You have instanton type contribution that goes like e to the minus square root of q. And the instanton action is a multiple of 2 pi. Okay. Of course, these are actually compatible with all the Monte Carlo result, because they are all small enough at unit charge that they don't spoil the leading scaling. So that is actually something that one has to check, and fortunately that was the case. However, these all have to multiply by a constant, which needs fixing somehow. And of course, if it is parametrically too large, this might spoil this estimate. So one has to find a way to fix it in this
Okay, here you froze again.
case. We actually found two different. Now I'm almost at a part with only figures, so this should
very good.
Be even easier. The bit that I actually wanted to show you is via word line path integration. So this goes as follows. You have non-perturbative definition of a heat kernel trace. It's just simply the sum over all path given initial and final conditions, which now coincides in order to form a loop. And this expression has a saddle point approximation in terms of instantons, if you want, which are just closed sphere geodesics computation for this resurgent constant. So I just flash the end result. You actually can compute at leading order the saddle point approximation, and you nicely find that there are some negative modes that deform my great circle just by pinching a little bit back one of the two. These are unstable, so they made all of these contribution to come with an I, with an imaginary part, which is slightly kind of important in what comes. You have a zero mode, which is just a rigid rotations of great circles, which gives you a different scaling with respect to the perturbative part. And in principle, you have other massive positive deformations, which gives you a fluctuation series. And the instanton action is just those integers times 2 pi, which are just the length of great circles. So this check actually provides you gives you estimates for all these ambiguities. They can all be fixed uniquely, and you can get a Borel resummed result for your gram potential. This result actually is, can be compared with a small charge expansion, which doesn't need any resummation because it's convergent, and actually can be matched up to arbitrary high accuracy. So it actually holds for any possible chemical potential. So maybe I can just, before concluding, I can tell you something about what one could expect at finite n. Actually, one can say, okay, but what if we assume that actually you always have a perturbative expansion which is asymptotic, regardless of large n? And now, after this new interpretation in terms of word-line path integrals, what if we just assume that also the leading singularity in the Borel transform comes exactly from this sort of physics, the one of a first quantized particle with a mass proportional to chemical potential moving on the space manifold, for our case, just S2. This is actually pretty nice because there have been found some of these particles once you do these large charge EFTs for non-abelian groups. So actually, just by scaling argument, then the form of your result is actually fixed up to an overall constant, which in our case we would say that is unity at leading order in large n. But the only two scales that you have are the length of great circles and the breaking scale of your EFT that goes exactly like square root of q in 3 dimensions. So in this sense, one can attempt or conjecture a form of a trans series for arbitrary n, which actually has a very similar form to the one in large n that you just found. And these also, recall, all of these is because as soon as you find such a trans series form, you can attempt an extrapolation to small charge. And even if we are interested in this large charge regime, if you want experimentally, the small charge operators are the one that can be probed. Okay, so it is a relevant part of the spectrum, but the one with small charge, if you want, might be of more immediate use. So let me just then jump to the conclusion before I freeze again. And so the main results of this work was just to notice that you have a large charge limit in the O2N Wilson-Fisher CFT, which is factorially growing and grows faster than a simple factorial, which is actually the growth that you find in orderly QFT. The growth of Feynman diagram is usually just factorial, normal factorial, but this is squared. Moreover, we also found what are generating this factorial growth, and these are known in the literature as word-line instantons, and in this case are all unstable saddles of a quantum mechanics path integrals. These are all unstable because there is no topology protecting them. We're not on a torus, we're on a sphere. Moreover, we also saw what is the set, at least the leading set of non-perturbative correction that comes into play and that are relevant here. And I actually, at least in large N, we show that they only depend on the sphere geometry. So there is no further input, apparently, other than the geometry of the space manifold. So, and with these, I think I can just conclude, and thank you for your attention. Hopefully it was not too painful with the freezing and everything.
No, don't worry. So thank you very much. Let's thank the speaker for this wonderful talk, despite the technical difficulties. And yes, so now we have some time for questions.
Maybe I can ask a question.
Yes, please go ahead.
So here you talked about two-dimensional spheres. So would there also be, or can you say something about, say, higher dimensions?
Yes. So you can, if you go to odd dimensional spheres, so you stay to odd dimension, then these analysis follows through quite similarly. You would expect from, at least from these argument, to have, however, different non-perturbating contributions. From an EFT perspective, the EFT scales as a square root of the charge only in the equal 3, and it will scale slower in a higher dimension. So you might find a different behavior here. This is something that we are checking numerically, because this is just an argument, right? Well, computation. If you go to even dimension, there is a further complication, namely that you need an extra regularization for these ground potential, because these theta functions are all hitting a pole there, simply because you have anomalies. So you need a further things there if you want. There are something more which I'm not really sure how to deal, but I think there has been work on that. So not in the non-perturbative sector. So, hope, yeah.
Thank you.
Other questions? If not, then in the meantime, maybe I can ask a question. If you, so it's like just some small things. If you go to your last slide again, please.
Yes.
Yes, exactly. There you say that basically you have this correction, right, which scales as the exponential of the square root of q over n. And you were talking about this double scaling limit that q is still dominating over n, right? So q and n goes to infinity, but q goes faster to infinity. Can you tune it such that, first of all, they're kind of going like that the quotient q over n is like a constant? And the second one would be like, can you also tune it in such a way that n actually grows faster? Because then it seems that these corrections would die out.
Yes. So completely, to be completely honest, actually, what is really important, what it really makes all of this implication here is large n. So actually, you know, you were able to find an expansion also when the charge is actually very small compared to n. And you would able to find out a convergent series, right? So over there you have some information, and you have also access to that regime. So as long as n is very large, you can take q to be whatever you want, right? And this result interpolates all these regimes. Now, of course, if you interpolate to small q, these are, I mean, this becomes relevant, but if q becomes larger, right, it becomes more and more suppressed. So the only real problem in this double scaling would be to go away from large n. So that would be the only, because you lose completely analytical control, basically.
I see. So it's very important that n is actually very large.
Yeah, to make this sort of study, yes, because it's simply because you need these coefficients of this expansion tail. And in the Monte Carlo result, well, they can estimate them numerically, but they cannot really reach, I don't think it can be possible to reach the order that you would need to make these to obtain these results just numerically, right?
Okay, thank you very much. I would have another small question about this grant potential. So you said like in 3 dimensions, it's basically giving you the Casimir energy of S2, right? So you get the zeta function or the Swirlitz zeta function of the Laplace on the sphere. Is this a general result? Like if you go to higher dimensions, let's say 4, and you compactify such that you have S1 times S3, let's say. The grant potential will always be this kind of Casimir energy?
Sort of, yes. Basically, yes. Actually, if you would keep also the thermal circle, because in what I showed you, I integrate that out.
Yes.
Just because I want to take the small temperature limit in the end. So you integrate that out and it's equivalent to a dimensional reduction. But if you would keep it, you really would get sort of a Casimir energy now on the compactified cylinder of for these particles with a mass proportional to chemical potential. These should be a general statement.
Okay.
It should be a general statement, and then you're gonna need basically to build this trans-series expansion for the corresponding zeta function regularized results.
I see.
But yeah, it should be sort of general, just because it comes, if you want, from the fact that large n at leading order makes the model completely Gaussian.
I see. Okay. Thank you.
No problem.
Other questions? Okay, so far I don't see any. So if there are no more questions, let's thank the speaker again. So thank you, Nicola.
Yes, thank you.
And I will stop the recording.